Hey folks, welcome back to Pre-Calculus. Today we're going to be continuing with section 2.4, which is talking about the values of the 6 trig functions. And we're going to be doing that by looking at a blast from the past with your special right triangles to figure out the exact way to find these functions. So you will be able to check using a calculator, but I'm going to teach you how to find all of these without a calculator. That way, you know you're right and you have the exact value instead of a decimal approximation. Let's take a look. So our goal today is to find the exact values of trig functions for specific degree measures. Remember, when we talk about exact, we mean fraction. Normally involves radicals. And at no point does it involve rounding. No rounding whatsoever when we're talking about the exact values. So, here's an example of it. We're going to find all the values of theta from 0 through 360 for which the 6 trig functions we've studied are equal to 1. And we can do that by first finding out sine, cosine, and tangent. And then we're going to use their inverses to find the rest. So, let's start with our circle. Sine is our y values, our vertical values. So here at 90 degrees, sine is equal to 1, sine is equal to 0, sine is equal to negative 1, sine is equal to 0. So this is only at 90 degrees. So now if we do this for cosine, cosine is my x, my horizontal value. So I'm at 1 here at 0 degrees, I'm at 0, I'm at negative 1, I'm at 0, I'm back at 1. So this is at 0 degrees, and for the sake of completeness, I'm also going to put 360 degrees. Now, where is tangent equal to 1? So tangent is equal to sine over cosine. So we need to take a look at that. Where they're the same, it's going to equal 1. And that's going to happen here at 45 degrees. Not going to happen here. Here it equals negative 1 because the x and the y are the same value but different signs. Here at 135 degrees, 215 degrees, it would also equal 1. Boom. So we have 45 degrees and 215. And if you're wondering why, that's because here x and y are the same. Because this is 45 degrees, so this is the same, and this is the same. We're going to talk about what they are in a second. Here, same deal. This is 45 degrees, so this is the same and this is the same. So that means that the coordinates, x, y, u, v, whatever you want to call it, are the same as well. Now, our cotangent, secant, and cosecant are going to be 1 at the same values. Why are they going to be 1 at the same values? Because all they are is 1 over the original. So we know that sine goes with cosecant, so this is just 1 over sine. Sine is equal to 1 at 90, so cosecant is equal to 1 at 90. Let me do that in green just so it really shows up and shows the connection. And then we have cosine is 1 at 0 and 360, so secant is also 1 at 0 degrees and 360 degrees. And tangent is 1 at 45 and 215 degrees. So cotangent is equal to 1 at 45 and 215 degrees. And we're done. We found it. But now what do we do when it's not equal to a nice, easy to interpret number like 1, which is happening in our axes? Well, that's what we're going to do now. And we're going to do it with a blast from the past. Now, this is a 45, 45, 90 special right triangle. You studied them in geometry. You may have studied them in Algebra 2 as well. They have a nice relationship going. Because it's 45 degrees and 45 degrees, this is isosceles. So that means whatever this is, this happens to be the same thing. And if we did the Pythagorean theorem out, you'd find that whatever this x is, x times radical 2 would be the hypotenuse. So if this was 1, that was 1, this would be 1 radical 2. If this was 5, this was 5, this would be 5 times radical 2. That's one of the properties about the 45, 45, 90. And we're going to use that in a second, and it's actually going to help with that thing about tangent, cotangent we just saw. Now we also have another blast from the past, the 30, 60, 90 special right triangle. And that also has special properties. Whatever this is, the hypotenuse is twice it, and the longer leg is that times radical 3. So if this was 1, this would be 2 times 1, so just 2. And this would be 1 times radical 3. If this was 5, this would be 5 times 2, so 10. So this would be 5 radical 3. And no matter what you end up choosing for x, you can follow the same pattern. And we're going to use this again to find some other measures of specific degree angles. And because this gives us radicals, we're able to then use it to get exact values. So here's an example of one of the exact values we're going to find. I want to find the exact value of sine of 45 degrees. Well, first things first, draw it out. So I know 45 degrees is right here. So I know this is going to be my ray. Cool. Now you might be wondering, okay, but I don't have a coordinate here. I don't have a point. What can I do? We can pick any point on this. And in fact, here's where I'm going to use my special right triangles. So I'm going to just pick some random point here. And we know this has to be a right angle. Well, if this is a right angle, and this is 45 degrees, means that the remaining one is also 45 degrees. All of a sudden, we have a special right triangle. Well, that means that both legs can be the same thing, and that also means that the terminal ray is going to be radical 2 times that same thing. So I'm going to make my life easier. Call that 1, call that 1, call this 1 radical 2. You could also just knock the 1 out and just call it radical 2. So if I want to find sine of that, I know that sine is equal to my opposite over my hypotenuse using SOHCAHTOA. So I can say that sine of 45 degrees is equal to the opposite, which is 1, over my hypotenuse, which is radical 2. And that's sine of 45 degrees. It's the exact measure. Now, why is this more exact than, say, plugging into a calculator? Well, I'm going to show you that using Desmos. Scientific calculator for Desmos. You can tell it's not the graphing because 1, it doesn't have a graph, and 2 up here instead of calculator, it says scientific. And what we can do here is I'm just going to plug in sine 45, and it's in degree mode because it says deg right here. If I were to click it, now it says rad for radian. However, right now, until I say otherwise, we're working in degrees. If you also want, you can type a little degree symbol. It won't pop up though. So sine of 45 degrees is equal to 0.70710678112. Well, that's not very helpful. But I can say 1 divided by radical 2 to check my work. Same exact decimal. The reason why this 1 divided by radical 2 is more exact is because even though Desmos is a powerful calculator, it's still rounding to get this. This decimal doesn't end. Desmos just has something in its programming saying after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places, it rounds the last one and stops. Because this radical 2 is an irrational number, it never ends in its decimal approximation, nor does it repeat. So this is able to express sine of 45 in 2 characters, 3 if you happen to count the radical sign. And it does it exactly. This can't even approximate the whole thing, even though it has 10 characters. So that's why we're going to stick with the fractions here. Let's take a look at this one. Cosine of 135 degrees. First things, let's draw it out. 135 is around here. So this is my terminal ray. Well, if that's 135, we know that this remaining part right here has to be 45 degrees. Which means we can do pretty much the same thing we just did. 1, 1, and radical 2. Awesome. The thing to keep in mind, though, is we are in quadrant 2. Because we're in quadrant 2, we need to make our x negative. So I'm going to make this a negative 1. Now, after that, I can just do cosine the way that we've been taught to do it. It's going to be my adjacent over my hypotenuse. So cosine of 135 degrees is just equal to negative 1 over radical 2. And you got a bunch of different ways you can write it. You can write it as negative 1 over radical 2, or you can write it like this, and you'd be good to go. We typically don't make the radical 2 negative because that's dealing with our radius, which we're always going to make positive. But either one of these, good way to write it. Let's take a look at this one. We got cotangent of 210. First step, draw it out. 210 ends here, so there's my terminal ray, which means that this is my reference angle. It's 30 degrees. Well, if that's 30, that means this is 60, so that's 90. Then I can go ahead and label my points. Well, 30, 60, 90 says that this is 1, this is 2, this is radical 3. I'm in quadrant 3, so it means that's negative and that's negative. So, now time to look at the cotangent part. Tangent is opposite over adjacent. Cotangent is the flipped version, so adjacent over opposite. Well, the adjacent here is going to be negative radical 3. The opposite is negative 1, so I can write my answer here as just a radical 3. The negatives cancel out. And again, I can express my entire answer using just radical 3. I don't have to get a decimal approximation or any nonsense like that. It's a much more concise and exact way of getting my answer. Awesome, we've seen how to do it with special right triangles. We know the special right triangle ratios. Just know to keep an eye out for those negative signs depending on what quadrant we're in. A diagram always helps. So head on over to the textbook. You're doing textbook problems today. If you have any questions, you can definitely ask them here in the chat or in the Zoom or the video. You can ask them verbally, you can ask them written, whichever. And I look forward to answering them. All right, folks, have a great day. Talk at you soon.